So, good afternoon, everyone. We are going to start today's session, and that is on Cox proportional hazard analysis. So, till now, we have learned some basics of survival analysis. What is survival analysis? What is time to event data? I'm just summarizing few key points before we move to Cox proportional hazard. Then we have understood that whatever time we measure, that is in the form of a survival time, that ST is known as the survival function, and there's a HT which is known as the hazard function. There are some other key words like there is a censoring, and that censoring is a unique feature of this survival analysis that it caters to all those data which is censored also, unlike the logistic and linear regression. That's the unique point of this survival analysis or the time to event data. Then we have learned the types of censoring. There's a interval right and left censoring. The most common type of censoring is the right censoring, which we usually see in case of health or the research. There are various types of research design where we follow the survival analysis. Most commonly, it is the prospective study design. That means longitudinal, where you are following a particular set of people for some duration. And again, you can also do a survival analysis in case of a or this time to event data analysis in case of a randomized control trial. Then coming to the life table analysis, when you have got a interval period with you where the event has happened and you don't have a specific time period when that event happened, then the choice of preferred analysis is the life table method, which the actuarial science generally they use it, like the insurance people. In health also we use it, but after the advent of Kaplan, Meier and Cox, the use of life table has decreased. But still we know the use of life table, how we calculate the at risk or the risk set, where in case of a life table, in the same row, you deduct half of the censored individual from the risk set because you assume that they were with you till half of the period. Whereas in case of Kaplan-Meier, you calculate the survival probability more than equal to that time t, and then you deduct all that individual who were above that particular period from the risk set. And that survival time you calculate, you write that whatever the percentage comes, you write that these many people survived up till or more than equal to 6 weeks or 8 weeks, wherever you are calculating the probability of the survival. Again, we learned that these survival probability is calculated only when the event is happening. When there is a censoring, the same probability will be applicable for the censored individual. So whenever there is a censoring, we don't calculate the survival probability because there is no hazard. And the hazard is again the failure. So the event, we also call it as a failure or a hazard. And for hazard and today we'll talk more of hazard. Till now, we have not talked of hazard because this Cox proportional hazard analysis, where it gives you different model, it works on the principle of hazard, where it calculates the hazard between the two and it gives you a ratio which is known as the hazard ratio. So all the interpretation of this Cox proportional hazard analysis will be in the form of a hazard ratio. So Kaplan-Meier, we have seen that you calculate the survival probability, and that's the cumulative survival. That's why you see that that is again a conditional probability. So the Kaplan-Meier product limit estimator method based on the conditional probability, that if you have survived up till this time, then what is the probability that you will survive to the next year? So that conditional probability and what is that cumulative probability you have seen. We have also learned what is why we use the median survival time in case of a Kaplan-Meier, why we don't use the mean survival time instead of median. We have also learned regarding the various assumptions of Cox, Kaplan-Meier. We have seen that there should not be secular trend. If there's a secular trend, how we can deal with that secular trend, doing the separate analysis of the two time point. We have also seen what is the informative and non-informative censoring, and we want our censoring to be non-informative. We have also learned that whenever you are trying to plot a survival curve using Kaplan-Meier, you should check the amount and pattern of censorship. It should be nearly equal, and pattern means like it should be random during the entire period. Otherwise, if there is a change, then again it may underestimate or overestimate your overall survival probability. We have also learned the Will-Rogers phenomena, where we have learned that if there is a change in diagnostic accuracy or treatment over the time, how it can lead to a false impression that there is an improvement in survival time, whereas in actual there is no improvement. So you should take care of these things whenever you are doing a survival analysis. Now coming to today's session, that is your Cox proportional hazard analysis. So for this, we are using this article, which is the breastfeeding education, early skin to skin contact, and other strong determinants of exclusive breastfeeding in urban population. And it was a prospective study. So suppose in this case, if you want to see like effect of mother marital status. So I'm taking the independent variable as a marital status, and my dependent variable is the time to event data and the whether the termination of exclusive breastfeeding happened or not happened. So if I use the Kaplan-Meier estimation, so I have got these curve, and we have seen this I think on Saturday. We have learned regarding the Kaplan-Meier, and we have also seen that if the curve which lies above they have got a better survival probability. And we have also learned that there are various types of statistical tests. Log rank is the most common, which generally measures the difference between the two survival probability in the later part. Then there is a Breslau's test, there is a Taro-Venn test, and all these tests, they are also useful when depending on when you want to compare your survival probability in the early part, in the middle part, or during the later part. So other named tests are again a variant of log rank only, where they put a different weights to calculate the p-value. So this is your unadjusted survival curve for marital status, and you can see here that the green color, the graph which is in the green color, that is having a better survival probability, and the green one are like others. Others means they are not single. Single means that those mothers were single, and in case they have got a better probability, survival probability. This is again a unadjusted, and we are writing this unadjusted survival probability. Why we are writing unadjusted? Because here we are only taking one factor. When you take more than one factor, then we call it as a adjusted. So this is an this is unadjusted survival probability for the levels of mother, and here we have taken the exclusive breastfeeding. So whether the child was exclusively depending on the education, this higher or lower education. So this provides again a clear representation. This yellow color you can see here, that this is giving you this orange or yellow, whatever you say, the lower, if the women were having lower education, they were having better survival probability. So can we think like mothers who are having higher educational status are more in single marital status, and that's why effect which we are getting for a single status may be due to the higher education status of mother. Because if you see these two curve, the first one says that the survival probability was bad for single mother, means compared to the mothers who are non-single, and here it is saying it is not so good for higher education. So I might think that the women who are in the higher education, they are more likely to be single. So is there any confounder effect of education on the status of mother using who are single? So if I want to understand the independent effect of this mother's educational status or marital status, then I need this Cox proportional hazard, similar to the logistic regression. If you can recall logistic, where you do the unadjusted and adjusted, so in unadjusted you only see with one factor, whereas in here, in case of a Cox proportional, it gives you the adjusted. It has got an option. You can have an unadjusted hazard ratio also, like in this case you can see. So you can enter all those variables and you can see the effect. So this then in that case, the Kaplan-Meier method will not be applicable when you want to see the adjusted survival curve, or you want to see the effect of one variable taking care of other variable. That means control for the confounder. Then you need to go for this Cox proportional hazard model. And this model allows us to include many other variables, be it even if the independent variable is a categorical variable, because Cox proportional, if you can recall the Kaplan-Meier, it doesn't work for continuous variable. It only works for categorical variable. So if we want to, eliminate all those limitations of Kaplan-Meier, then we need the Cox proportional. So there are some limitations of Kaplan-Meier. What are those limitations? So the first limitation that we have just discussed, that there are no option of covariates. That means you cannot compare many factors together and there is no adjustment. The second limitation is it cannot model the continuous variable, because if your variable is, let's say, age, or if your variable is the number of educational sessions, so in that case, since it is not a categorical, you cannot do it in case of a Kaplan-Meier. Kaplan-Meier only works for the categorical, not for the continuous. And again, it doesn't give you effect size. Effect size means we are talking in terms of hazard ratio. So it only tells you the survival probability or the cumulative survival probability of the each group separately, but it doesn't tell you the comparison in terms of like effect size, the way we take out the beta coefficient, or in the logistic regression, it's the odds ratio. And it does not explore interactions also, because in case of a Kaplan-Meier, you cannot explore interactions. So those are the limitations of Kaplan-Meier, for which there was a newer mathematical technique which was invented by Cox, and that was named as the Cox proportional hazard model. Now, what is this Cox proportional hazard model? This is a very important, because we have learned that this time to event data is a it's a skewed. That means it is a non-normal data. So Kaplan-Meier, that's a non-parametric. But if you see this Cox, this lies between the parametric and non-parametric. So that's why we call it as a semi-parametric. And that's the beauty of this Cox. And we will learn later that why this Cox proportional hazard is so much popular. Even if you see that in survival also, you will see very less of papers being documenting the parametric model of this survival. Generally, they use Cox proportional hazard model, and we'll discuss why this is so popular. And it estimates the effect of multiple predictor, because we know that if there are many covariates, both categorical and continuous, you can control for all these covariate in case of a Cox proportional hazard model. And it models the hazards ratio. So the output or the interpretation which we see in case of this modeling, it's the hazard ratio, and it's independent. It's the confidence interval of the hazard ratio. And like I said, that it works both with the categorical and continuous data, and it quantify risks with the hazard ratio. So this is the formula of Cox proportional hazard model. I'll just explain it a little bit, because it may sound too much of mathematical this thing, but this equation is important. And we'll explain towards the end also why this equation is important. If you see this equation, it tells you like this is the hazard function at time t. And this x is your predictor, like x1, x2, x3, they are all predictors, like the factors which we have seen. It may be the marital status of mother, it may be the perception of milk production, literacy status of mother, or the number of health education received in the prenatal period, or the gender of the baby, or whether they have received the skin to skin contact or not. So all those factors are the predictors. They are the independent variable or the predictor. And this H0T, this is known as the baseline hazard. So this H0T is the baseline hazard. And this is important because they say that it is unspecified function of time. Unspecified function means if like it's a mathematical term, unspecified, but you just remember that this is the baseline hazard, and here there is a unit of time. Time t is there, and then this dot is a multiplication. So then it is multiplied by exponent. So if those of you who have attended the logistic regression, you know that there also when we calculate the odds ratio, we take the exponent of the coefficient. Remember, and then not we take means it gives actually. The software gives, but we have just checked it. Like if you take the exponent of that coefficient, which is the beta 1, this beta 1 is the various coefficients. It gives you the hazard ratio of that particular variable. So this H0t is the baseline hazard, and this HTX is the hazard function at time t. And this beta is the regression coefficient for each covariate. And this exponent of beta, that is the hazard ratio. And if it is a continuous variable, so hazard ratio for 1 unit increase in the continuous variable. So this is the equation. So if you can recall the logistic or linear, here the function was plus. Plus means like it was like one intercept plus we used to multiply beta 1 x1 plus beta 2 x2 and so on. But here it's slightly different. If you can recall that, then it is h0t multiplied by exponent of this. So we take exponent here only. And that's how the Cox proportional hazard model, we write, and it works on this principle. That means if in the statistics or if in the Jamovi, if you are running it, it uses this mathematical formula to give you the hazard ratio. So the interpretation of hazard ratio, it is again similar to the odds ratio. If the hazard ratio is less than 1, we say that the hazard, particular hazard of that factor, it is protective. That means it is less on the people who are exposed as compared to the non-exposed. Non-exposed if we take as a reference. Then if it is more than 1, we call it as a risk factor. That means higher hazard in the people who are exposed as compared to the reference. And if it is 1, then we call it as a no effect. So it is exactly similar to the odds ratio. Even the interpretation is exactly similar to the odds ratio. So now coming to, there are two types of, so we have seen in the Kaplan-Meier about the unadjusted survival curve. But in case of a Cox also you will have the adjusted survival curve. So what is the difference between these adjusted versus non-adjusted survival curve? So the curve which you get from the Kaplan-Meier, that is your unadjusted survival curve. But the curve the survival curve which you get from the Cox proportional, that is your adjusted survival curve. And in case of, if you just want to have a raw comparison, initial analysis, then you may go for this Kaplan-Meier. But if you want to use for for more sophisticated analysis where you want all the control of confounding, then you should use the Cox proportional. Again, in case of a Kaplan-Meier, you cannot see the isolated effect of one variable because it is again only, you can enter only one variable at a time. But in case of adjusted curve, you can have isolated effect of one variable. So Kaplan-Meier, if you see this adjusted curves gives you a real world mix where nothing, you can say that yes, I think it's this real world mix will be given by your adjusted curve, not the Kaplan-Meier, because Kaplan-Meier is not the standardized one. So now coming to the adjusted survival curve for marital status of mother, termination of exclusive breastfeeding. So this initial two, you have seen that we have got the unadjusted where the women who were like non-single and having a low literacy were having better survival probability. But if you get an adjusted survival curve, you can see here that, if those others are still a better survival. That means as compared to the single mother, the women who were non-single, they were having the better survival probability of the termination of the exclusive breastfeeding. So we can say that this is not getting confounded by the literacy. That means which we were thinking initially. So now you have this independent effect of this variable, which is your marital status, that is single versus non-single. And after adjustment, we found that, so what was my initial observation? That the single marital status, they breastfed exclusively for shorter period. It is valid after controlling for education, baby gender and other factor. So it will suggest that the marital status is an independent predictor of the exclusive breastfeeding duration. So now coming to the adjustment, again, this adjusted Cox regression, adjusted survival curve, we have retrieved or we got through the Cox proportional hazard model, where we have entered both these variables together along with the other variable, and it has given you the output for a single variable. Now, the one is again question that why relationship change after adjusting for the other variable in survival analysis, because you know about there is something known as the confounder. So you know that there's a confounder and there's a effect modifier. So the in case of a confounding, you know that this confounder is related both to the outcome and to the exposure, and it is also, it causes the independently, it also causes the, it is again a risk factor for the disease. So you, if you want to see the independent effect of a particular variable, you should control it for the confounder which you are expecting. Again, in case of a logistic regression, we learned that the basis of identification of which variable you have to put in the model, that should not be only on the basis of statistical significance. If you remember, in case of logistic, we always talk that the p-value, you only take those variable in the model where the p-value was up till 0.2. We become more lenient in selecting those variables, but it is, this decision is not only statistical. So number of variable to be, what do you want to like number of variable you want to keep in model, that should be guided by your theoretical perspective. That means you have read the literature, you have experience. Those are more important criteria, and then of course you will supplement that, or you will augment that decision with the help of statistical method. But it should not be only statistical method of taking which variable to be put in your model. Again, this it adjusts for confounding, including confounding variable as a covariate in other model, and hazards ratio, which is also called as the adjusted hazards ratio. The way we used to call it as a adjusted odds ratio. You remember crude odds ratio versus adjusted odds ratio. Similarly, here you will see that it is a crude hazard ratio and the adjusted or unadjusted versus adjusted. So this hazards ratio which you get from this multiple, when there are multiple covariate, this Cox model estimate the hazard ratio for the primary exposure while holding the other confounding variable constant. That means it calculates the effect of that particular exposure variable as if all the study subjects were same in respect to other confounding variable. That means we will see that in more in the interpretation, it keeps other variable as constant and it will only show constant. What do I mean? That means everyone is having the same level of that particular variable. And then it calculates the independent hazard ratio for that particular explanatory variable. So now coming to the assumptions of this proportional hazard. So one of the very important assumption of this proportional hazard regression is the assumption of proportional hazard. So there is a term which is proportional. So what do I mean by proportional? So proportional means even if the individual hazard is changing, if you take out the hazard ratio, that does not change over the study period. That means if there is a study which is of duration of, let's say in this example, it is of 6 months, or if you are following the individual for 1 year, then also if hazard may be different in two groups, but if you take out the ratio over the time, it should be constant. It should not change. We will explain it with few examples. And that's the concept of proportional hazard, that it requires that the hazard ratio is constant over time. That means the hazard ratio of one individual is proportional to the hazard of any other individual. So this is one example. Suppose we are comparing the treatment A and treatment B, and the outcome or the failure is the relapse. So if you see the hazard, this is your the first column is the time. So this is the independent time. So this is the hazard at 2 weeks, 5 week and 10 week. So if you see the hazard in the control, this B is the B group is the control group and A is the treatment group. So hazard is more in the B, which is because it is control group. So it is 0.1 here, but it is 0.05 here. But if you take the hazard ratio, which is A to B, A divided by B, then it is 0.5. Then again, if you see the hazard at 5 weeks. So at 5 weeks, now the hazard in this group B is 0.06. And hazard in group A is 0.03. So hazard is different with the time. But if you see the ratio, it is constant. Similarly, if you see at 10 weeks, the hazard in control group is 0.04 and the hazard in treatment group is 0.02. But if you see the ratio, it is again 0.5. So what do I mean by that? With the passage of time, like the time is increasing 2 weeks, 5 weeks, and 10 weeks. With the passage of time, there might be change in the hazard in the two group. But if you take out the ratio, it will be here, it is showing exactly same, but it is nearly same. So that is the proportional hazard assumption. For example, here if I'm comparing the hazard in male versus female. So if I've started this is the female group and this is the male group. So suppose if my start time is this, at 3 months, the hazard is 1.5. So this is like 1 and 2 means the hazard is twice here. So what will be hazard here here in the male at 3 months if my proportional hazard assumption is met and I say that it will be constant. So what should be the value of hazard here in male at 3 months? Yes, all of you please type in the chat box.
3,
3. Very right. At 3.5?
7,
Yeah. Then 3.8?
7.6,
Yes. And then at 12 months, sorry.
8.8.
8.8. So rightly said, it will be 3, 7, 7.4 and 8.8. That means even if the hazard is different in these two groups, over the passage of time, the ratio will be constant. Hazard ratio will be constant. Similarly, we are trying to explain this concept with another example, that is on effect of gender on the second attack of myocardial infarction over a period of time. Then at start, if it is like at start it is 1 and then 1.2. And again at 3 months, if you see, it is 2.2 and 2.6. Again, if you see at 6 months, it is 3.1 and 3.7. So if you calculate the ratio, you calculate the ratio of 2.6 versus 2.2. Yes, all of you please do that and type in the chat box. What will be the ratio of these at 3 months? 2.6 divided by 2.2. I will also do along with you. I can do it here also. Let me 1.18. So it is nearly like 1.2 you can take. And then if you calculate like 3.7 and 3.1. So if I do it like 3.7 divided by 3.1. So it is 1.19 or 1.2 you can say. Again 4.2 divided by 3.5. So 4.2 divided by 3.5. So this is again 1.2. So again the same example that the ratio is changing, but you can see here that, the individual hazard is changing, but the ratio is constant. So in this example, we can say that the effect of gender on the second heart attack is same across each time point. Similarly, if you consider this example, so here you will see that hazard ratio is now changing, but again nearly same. It is not exactly same. So if you take out the ratio 2.5 versus 2.2, 3.5 versus 3.1, 3.9 versus 3.5, and 5.2 versus 4.6, then also you can say that it is nearly same. You can calculate it. I am not doing it right now, but it will be nearly 1.2. So in that case, you can say that the effect of gender, it is not exactly same, but it is nearly same across various time point. But if I calculate this, suppose, so let me do this because now I need the calculator. So if I calculate like 3.4 divided by 2.2, so 3.4 divided by 2.2, it will be 1.54. Again, if I calculate 1.8 divided by 3.1. You can yourself see that the hazard is like changing. It is 0.58. So now it has decreased. So sometimes it will be more than 1, sometimes it is less than 1. Then we can say that no, hazard ratio, it is not constant with passage of time. That means at start it was 1.2, at 3 months it was something else, at 6 months it was something else. So all the hazard ratio is changing over the passage of time. And then we say that the proportional hazard assumption is not met in this case. Why? Because the hazard is changing. In that case, you can't take this variable into your analysis. It is exactly same. Can you recall the ordinal logistic regression? Those of you who have attended the logistic regression, or you know also beforehand the logistic regression, there also there is assumption of the proportional odds, that it will be same across each level. Whenever we move from a lower to higher category, the odds will be same. That's why it gives you one odds ratio in case of a proportional odds, whereas if you apply the multinomial logistic regression, you will have those many. It gives you n minus 1 model, so you will have 2 odds ratio for each taking as a reference. So the not exactly, but very much similar, because there in case of a proportional hazard, the time component was not there. There the proportionality we were measuring when we were moving from the lower to the higher level. Here the proportionality concept is related to time. That means when we are moving across time, means when we are seeing like you are moving ahead of time, at each time point, the ratio of the two hazard, that is the hazard ratio, should be constant. Am I making sense to all of you up till this point? You don't have to check it. There is a test in the GEMOV which automatically checks for this proportional hazard. You don't have to do it, but just to have an understanding, what is a concept of proportional hazard? Am I making myself clear to all of you? Okay. Thank you, Priyanka. Thank you, Namrata. So we can say that yes, the effect of gender on the second attack of MI is nearly same in the previous one, but then again gender has a different effect on the second attack of MI in the third example. Then we can say that no, because it was changing. So that's the concept of proportional hazard. Now coming to the formula. Now a little bit of mathematical concept. So this again, I said in the beginning that we have used the Klinbaum, the first three chapters for making the content, and this screenshot I have taken from the Klinbaum only. So it tells you, it will, I mean, you don't need to like remember this formula. You just need to understand like why this proportional hazard is very popular and what is so special about this proportional hazard. So this is same which we have learned earlier, that this, if you see this HT, this we have learned this formula earlier also when in the beginning. HTX is the hazard function at time t, and this H0 is the baseline hazard, and this is multiplied by this exponent, and then you take in exponent beta 1 x1 plus beta 2 x2 beta 3 x3, where x1 x2 x3 are the explanatory variable. So this H0t, which I was telling, this one, this is a baseline hazard which involves the t, that means time, but it does not have this excess if you see the formula. And if you see this exponent, this one, this is an exponent, it has got these x's. X's means it has got these explanatory or predictor variable, but it is no, there's no there's no formula or there's no unit of time. So we assume that these x's means these all predictor variable, they are time independent. Okay, so that's one very important assumption. Time independent, that means with the time they are not changing. So that's why this proportional hazard assumption, it again, what it does, like it HT and H0, if you see this, if you move this HT here in the denominator, then this HT by H0, it becomes a constant. And that constant, if because there is no variable of time, that's why it remains constant. That's why it works on this formula, because this H0 and HT, if you see here, this is a constant, because in that exponent formula, here there is no variable where there is a unit of time. time variable is not there in that exponent one. That's why we say that it is a constant, and this H1t is the hazard in the exposed group at time t, and this H0t is the hazard in the unexposed group in the time t. And that's how, because there's no unit of time here, there's no unit of time in this exponent, this one. That's why all the hazard will be constant. That means hazard ratio, not hazard ratio will be constant across the time. And this is known as the Nelson-Allen estimate of the hazard function. So this constant, it is also known as the Nelson-Allen estimate of the cumulative hazard function, and it says that if the proportional hazard assumption is correct, then you plot the curve, and we will see that then there's a graphical representation. So the both curve will go very parallel. They are not going to cross each other. If they are lying parallel, that means the proportional hazard assumption is met. Have you understood why the differences in the unit, when there is one unit is time, the other in exponent, there is no time? And that's why, since it is constant, and that's why this proportional hazard works on this formula, and that's why it assumes that since there is no variable which is changing with time, that's why hazard will remain constant. Am I making myself clear to all of you?
But ma'am, at every junction or every point of time, the hazard will keep on changing.
Hazard will keep on changing, but not the
But
ratio.
the ratio.
Yes. Because this H0, H1 by HT, this is a constant. This is a constant. Why it is constant? Because it works on this formula. This formula where you are taking exponent, this exponent of this beta coefficient and this your explanatory variable. And there is no time, there's no variable of time here. That's why it is constant. That means hazard might change. But this ratio, H1t divided by H0t, and this is hazard ratio. That means hazard in the exposed group and the hazard in the unexposed group. Individual hazard might change, but not the ratio. It will remain constant. And that's the proportional hazard assumption. That's why we will see in the curve that if you see the hazard curve, it will go like this. It will be parallel. It will not cross. Whereas if this assumption is not met, these two will cross each other. It will be something like that. Or maybe if I draw it, it will cross like this. Okay, so this is the graph will go parallel. That means the hazard might change, but this Ht by H0, this will remain constant. Okay, thank you. And this is the Nelson-Allen estimate. So this Cox proportional hazard model, it is also known as the Cox proportional regression model or regression method. And again, initially we have discussed that the result is expressed that H0 by HT, HT by H0 is your hazard ratio, and this hazard ratio is interpreted in the same way as the odds ratio, the way we interpret the odds ratio. Now, you remember in this formula, we have talked about this, that there is no variable which is dependent on time. So can you name, so that means there are two variables. If you can see this, it is writing that x's are time independent. So now that means there will be few variables which are time dependent also. Now, can you give some example of time independent variable which will not change with time? Yes, all of you please type in the chat box. Any variable which will not change with time. Yeah, very right, Tanya. Gender. It will not change with time. Yes. Generally, they assume even the categorical, like if smoking status, let's say. Smoking status might change in between also. But generally, they say that smoking status is also, in majority of the case, it will be unchanged. Okay. And what about age? What do you think of age? Is it time dependent or time independent? Yes. So ideally, age is a time dependent. That means if you are following a study for a large duration of time, like let's say 15, then of course the age will change. That's why. But here, if you assume that you are taking age at the baseline as a predictor variable, then you assume this age also as a time independent. Okay. So now coming to the concept of time independent and time dependent. So all in case of a hazard, this Cox proportional hazard, you assume that all variables are time independent. Even if they are time dependent, you assume that they are time independent, and that's why you are calculating this proportional hazard. If the proportional hazard assumption is not met, that means that variable is changing over time. And then you will not include that particular uh, explanatory variable into your model. So coming to the assumption of time dependent and time dependent. So time independent variable, they are measured once at baseline and they are assumed to remain constant throughout follow-up period. Example like gender and like I said smoking status. Generally age and weight, there might be some changes, but typically we consider these as fixed or time independent in case of a Cox proportional. Even if the because we assume that we are taking these variable as a baseline means age at baseline, whether it affects or not, weight where whenever you affect it gets affected or not, and you check this again. We are not only going by subjective way that I think that weight will not change or I think that smoking status will not change. No, we have got an objective way also to measure this, and that we check with the this proportional hazard assumption or the pH assumption. There are some time dependent variables also which changes over time in the same individual, like blood pressure, treatment adherence, or any biomarkers. If you are measuring some biomarkers in an individual, that will also change over time. So if the proportional hazard assumption doesn't met, that variable is a time dependent. That means then you cannot go for a Cox proportional. There's another model which is known as the extended Cox. You have to apply that. So which we are not covering in this workshop. Probably we'll have another workshop where we can only have workshop related to extended Cox, that means time dependent variable, and other parametric survival method, because in this workshop we are covering the non-parametric and semi-parametric. Kaplan-Meier and life table are non-parametric, whereas this uh, Cox proportional is semi-parametric. Non-parametric we are not covering, and the extended Cox also. So this time, if the variable is a time dependent, which is changing with time, then you have to go for extended Cox. Now, coming to this, like in the beginning also, I was telling you that why this Cox model is so popular. You will see very less people going for like Weibull, and there's an increasing exponential, decreasing exponential. Those are the types of the parametric model. But most commonly, you will see people go for this Cox model in case of a time to event analysis, because the first important thing that it does not require any space of any specific shape of the baseline hazard function. So in case of a parametric, it is different from parametric, because in case of a parametric, you have to define like which shape of baseline hazard you assume. So that's why it doesn't need that particular assumption of that baseline function. Again, it focuses on relative hazard, that means hazard ratio. And one very important, if you ask from me, this is a very important point that they have tested, and you can read the Klinbaum, the second chapter, and not the second, sorry, the third chapter. And they are saying that even if a particular model is fitting to the parametric method, and if you apply this Cox, the values will be very much similar and consistent as nearly as your as nearly as your parametric. So they say, I mean, this line I have taken from exactly from the Klinbaum, that it will closely approximate the result of the correct parametric model. That means even if a model is particularly fitting to the parametric method, but you don't want to go for parametric method, then also you can go for this Cox proportional hazard, and the value of the hazard ratio or the output, it will be very much similar to the your parametric one. Okay, so that's why this Cox proportional is very much popular. Now, what to do when your proportional hazard assumption is violated? So, if any of the variable or the predictor variable, if it is not fitting into your concept of proportional hazard, in that case, you may have to go for extended Cox, or if you want to go for this Cox, then you don't include it in model, and there is something known as the stratification. So, you stratify if because generally you can stratify on the basis of either you can do it for the categorical variable. Suppose if gender is not gender is the time dependent. Suppose smoking status. If you are measuring something with a smoking status, or let's say in this example, mother's literacy status. So if it is not uh, going by the assumption of proportional hazard, then you can stratify. That means separately you take out the model for those two groups, or you can go for the parametric survival model like I was talking, or again you can break the axis into intervals. Remember that secular train, that means when on the day 2 we have done that in the 3 different quarters, or on day 1, remember we were talking about the leukemia example where the author have modeled the 3 separate leukemia period, like 60 to 65, 65 to 70, and 70 onwards. So in that case, you can break your continuous variable into a categorical variable into different time axis, and then apply and then propose the model for 2 intervals separately. So this was for the proportional hazard assumption, and the Cox proportional, the general how do we model the equation, what is the hazard ratio, what is the concept of proportionality over time, and what is the Nelson-Allen estimate. That means that ht by h0, it will be a constant. How do we check for that? So these are the important thing, and then there is an assumption. How do we check for that? So the first assumption is the proportional hazard assumption that we have seen, which is again it is done two ways. You can check it graphically, and you can check it objectively also. Remember, in case of normality also we talked that you can check the normality using both objectively as well as subjectively. Similarly, here also you can check it both objectively and subjectively. By graphical way, that gives you like log minus log curve, which is there in the SPSS. In case of Jamovi, again, it gives you the graphical as well as the objective. And this is based on a checking of something known as the Schoenfeld residual. Uh, Schoenfeld residual, what is this? We'll discuss that. But just remember, based on Schoenfeld residual, we calculate or we test this assumption of the proportional hazard. And then again, this is one of the very important assumption which we have learned in the logistic regression also, that multicollinearity. So multicollinearity, either you can check by the standard error value, or since in Jamovi you will see that this option is not there, so you can go back to the logistic regression, check the multicollinearity from that, and then you can apply the same here in the proportional hazard, because in the survival this option is not there. So now what is this Schoenfeld residual? So basically what it does, it again works on the calculation of observed and expected value of survival probability. So it measures the difference between the observed covariate value at a particular time and the expected value of that covariate at that time. And then it calculates the difference between that observed and expected. So under the Schoenfeld residual, it shows that with time, that observed minus expected, it will not show any trend. That means it will remain constant. We'll see in the graph. So under proportional hazard assumption, this residual, it does not show any trend. If it is changing systematically with time, that means it is showing that it is a time dependent. That means proportional hazard assumption is violated. There's a subjective, this was a subjective way. There's an objective way also when you have got a p-value. So this Schoenfeld residual, the Jamovi gives a individual value of p-value of this Schoenfeld residual. And if the p-value is more than 0.05, that means your proportional hazard assumption is met. That means your Schonfield residual value, the difference in the observed and expected. That means Schonfield residual value is not changing with time. That means the p-value will be more than 0.05. So this graphical, that means the movie plot this graphical residual versus time, and it adds a very smooth curve. So if there is a flat line, then the proportional hazard assumption holds. If there is a curvy line, then this assumption is violated. And statistical test, again, it's a global test. It checks the proportional hazard assumption across all covariate, and it gives you the p-value for each Schonfield residual. And if the p-value is more than 0.05, then you assume that the proportional hazard assumption is met. Am I making sense to all of you up till this point regarding the assumptions and regarding the concept of proportional hazard? Okay, Priyanka is saying yes. So I think it's 1 hour. So should we take a break of 5 minutes? Then we'll again be back. Okay, so we are coming back in 5 minutes. So we are back. So we were discussing regarding the objective way of measuring the proportional hazard assumption. So we discussed this. So I'm skipping this slide, the interpretation of hazard ratio, whether it is less than 1, 1 or more than 1. Again, the way we interpret the odds ratio. So if you want to express it in percentage, then how do you do that? You deduct 1 from that hazard ratio and multiply it by 100. If the value is negative, then there is a reduced hazard in a particular group. That means in your test group as compared to the reference group. If it is positive, that means there is an increased hazard. This is same as like more than 1 and less than 1. And then sign will convey the direction of increase or decrease, like plus or minus. If you don't want to convey it in percentage, then that particular value, you just say that the hazard was more 0.93 times more in your test group as compared to the reference group. This we'll see when we'll analyze the table and interpret the table when we'll do the regression, this Cox proportional regression. This is again one important, when you see the curve. So remember the survival curve. If you can recall the day 1 and day 2, we discussed that the survival curve is basically, it's non-increasing. And if you can remember, we have discussed that it is something like that. It is a step down function. It comes down at time t, at this, it is 1 when everyone is surviving, and then gradually it decreases. But in contrast to the survival, this hazard curve will be always increasing. Why? Because you assume whatever event you have defined, the event or the failure, that will increase over time. Let's say like this cessation of breastfeeding. With time, there will be more number of children where there will be no exclusive breastfeeding. If your event is death, with time the death will increase. If your event is like remission, stopping of remission in leukemia, then with time there will be more patients who will be relapsing. Similarly, so whatever event you define or which is a failure, that will increase with time. So the hazard curve will be like it is increasing like this. It will not be decreasing. And I think on day 1 we have discussed the functions of hazard curve also. What are the features? So like this is example of the hazard curve, and you can see here that there are two groups. So opposite to the this survival curve. In survival curve, remember the curve which lies up. If this lies up, they have got better survival probability. Here the curve which lies up, that means they have got a more hazard. So that's why here if dash is the placebo and this solid line is for atorvastatin. So what you can say that the atorvastatin group that has got a 36% less hazard of experiencing the event at any given point of time. If the hazard ratio is 0.64, see if the hazard ratio is 0.64, then you can say how you will interpret? What you do, HR minus 1. So hazard ratio minus 1. It will be your 0.36. 0.36 multiplied by 100 will be 64%. So 0.36 multiplied by 100 will be 36%. And since 0.64 minus 1 will be having negative sign, so you say that this group is having 36% less hazard of experiencing the event at any given point of time. Am I making sense to all of you? How it is different from the adjusted survival curve, where the adjusted survival, the upper curve has got a better survival. In case of a hazard, it is opposite. The curve which is up, that means more hazard. Since it is the event which is happening. So with time, more event will be happening. That's why it is increasing. So this was proportional hazard. Now coming to the multicollinearity between the independent variable, you can check the value of standard error. So if the value of standard error is ranging from 0.001 to 5, then you can say that this is, this multicollinearity assumption is met. But again, there's one way, that is the variance inflation factor, which we have learned in the logistic regression. So you can check from that also. If the VIF is less than 10, that means there is no multicollinearity between the variable. And if there is a multicollinearity, what is a multicollinearity? That means two variables are related to each other linearly. That means if you know one variable, you can know the value of another variable. That we mean by the multicollinearity. So now let's see the question and let's understand. So this is my data sheet. I will explain it once again, and let me open the question. And this reference article as well. So this data set, what we have created, this is taking this article as a reference. Breastfeeding education, early skin-to-skin contact, and other strong determinant of exclusive breastfeeding in an urban population, a prospective study. So if you come down, strength, if you read the strength and limitation of the study, so the author is saying that this is a longitudinal prospective study developed under the real life condition in an urban Ecuadorian population in the coast region of where the specs, Manabi province. A total of 363 mother-baby diet were followed up to a median time of 125 days. Data was collected at 3 separate times in 3 different phone surveys. A Cox proportional hazard model was performed to evaluate the independent association between each explanatory variable and the duration of exclusive breastfeeding. Several secondary analyses to assess the sensitivity of our estimates with our assumption. And the most relevant limitation was the lack of representativeness from the rural population, because they did not include the rural people. So if you see the statistical analysis and sample size. So sample size, generally, we have discussed this issue of sample size in logistic regression, where you can use the beta estimate to calculate the sample size, or you can use the effect size. So effect size, in case of the survival analysis also, the effect size is your hazard ratio. So you can use the hazard ratio, which is the lowest, and then you can calculate the sample size using that hazard ratio. You calculate it using the G power. And if you don't want to calculate it using the hazard ratio or the coefficient, then you can use like variable. That means if you want to model 5 variables, we generally take 20 outcome. That means like event happened per predictor variable, 15 to 20. And that way also, that's a rough estimation of the calculation of sample size. So they have calculated the samples. You can calculate it using incident rate also. They have calculated using incident rate of abandonment of exclusive breastfeeding, 2.8 event. And then you can see final sample. So they have first done the descriptive statistics using percentage for categorical variable, but median time and discrete variable. Then they have performed log rank test for equality of survival function. And then we estimated the crude and adjusted odds ratio for each explanatory outcome. And in that sense, they have built a multivariable Cox proportional hazard model to evaluate the independent association between each criteria. Again, if you see what all variables they have taken, so they have taken that based on the previous established criteria, we eliminated covariate having more than point P 2.5. So if you see, they have taken the P value of cutoff of P more than 0.25. If any variable was having a P value in the unadjusted. So this, how do we do? The same way we have done with the logistic. Initially, you do one variable at a time, check for the P value. The initial value also, again, I said that there should be some theoretical work before that, which variable to test, along with that statistical part. And then once the HR and the corresponding P value was calculated. And once the parsimonious model was obtained, then they compared both model to choose the final model. So this, there is a term which is can you see there's a saturated model. So the term saturated model is used when you have all the predictor variable. And the term parsimonious are used when you take only selected variable where the P value was less than 0.25. So that's the term generally they have used. And then again, they have written that they have estimated HR by mixed method. Okay. So missing data also they have written that there were missing value of less than 1%. So that's why they have employed complete case analysis. That means they have just did not take account of that because the missing values were very less. It was only less than 1%. And then to test for potential effect modification, they have done a stratification of the main analysis to infant gender. And then they have also performed many secondary analysis. So we'll show you. And then they have, this is the result. So result we'll see. First, let's see the data. So this is the data set. We are working on the same data set from day one. Still, I'll explain the data set. So starting from date. So this is the date of delivery. Then this is your date of termination of breastfeeding because we assume that's the follow-up time. This is quarter of the year. We have divided all these children in 3 quarters. This is gender of the baby, male and female baby. Marital status, that is the other and single. Education, higher and lower. Breastfeeding education, that's a continuous. That means number of hours of education session during the prenatal period. This is skin to skin contact, yes and no. This is breastfeeding within 1 hour, which is the early initiation of breastfeeding, that is yes or no. This is perception of milk production. So this is, it has got both the, you can treat it as a ordinal or a continuous since it has got 5 levels. So I will treat it as a continuous. So very little, moderate, enough and more than enough. The data sheet which we have shared there, it is in the form of a ordinal. So you can change it to the continuous by putting this number, but that you'll have to do it either in Excel or you have to put the command here. Then coming to the other variable, that is gestational age, again continuous variable, birth weight continuous. This is time to event. Again, time to event is a continuous variable because it is the total time, whether it is a censored time or survival time, depending on whether the child was censored or it was event happened. And this is censored and the termination of breastfeeding. So this is the data set. Now coming to the, yes,
Ma'am, how to divide it into quarters that you had divided in first, second, and third and fourth quarter?
that we did it in Excel, seeing the date.
Acha, manually each and every data, or we have to put any command and it will happen?
No, that just for demonstration we did it actually, but otherwise you can do it in your own. When you are collecting the data, then only you can create a variable. That particular date, suppose if your period is for 6 months, then initial 2 months, first 3 months, first, second, and third. You can divide
Okay,
it into 3,
okay,
just to
ma'am.
see any secular trend. So we did this later.
Okay, ma'am. Thanks.
Because if you have, like, you can do it retrospectively also, but suppose like in case of that leukemia patient, so they have study of entry of that particular child or particular patient in your study. So you can divide on the basis of year also, like year 1, 2, 3, depending on. So you can have a separate variable where you can have like create a variable from your original variable. Okay. Just
Yes,
to
ma'am.
see the time trend.
Mhm.
So now coming to the question. So we did the life table and we did the Kaplan-Meier. Now I have to conduct a univariable Cox proportional hazard for each predictor to assess their individual impact on exclusive breastfeeding. So this is my data set. I'll go to this survival. We have seen this survival analysis death watch. We have also seen this single survival for the whole group without explanatory factor. And we have also seen this univariate survival analysis and 1, 3, 5 year analysis. Now coming to this multivariable survival analysis. So I will click this multivariable survival analysis. This is again the same interface as logistic regression. That means, except that you have got two dependent variable here. That means you have got a time elapsed and outcome. Again, this box is same. One box for explanatory variable, which is ordinal or nominal, these two. And then there's a one box which is for the continuous variable. It
But
gives
ma'am,
you,
you had said time factor is not there. That will be only in extended Cox proportional hazard model.
yeah, that is there. But that I was talking, Dr. Ravi, in terms of the explanatory variable. So whatever variable I will take, which I will put here, that should be time independent. Without this you cannot, actually you were not there on day 1 and day 2, so that's why probably
Oh,
this is not clear. So this is your survival time. That means you have followed a person up till that time. Either that person is not there with you, that means lost to follow, which we call it as a sensor, or that person met with the event, child or person, which we call it as a failure. So this time elapsed means it consists of two times. Either it is a censored time or it is a survival time. And that's why survival data is unique. So this is must. Without this time, you cannot analyze, because this is your dependent variable. This one and this outcome. Because if you can recall logistic, if you don't have this time, if you remove this time from this window, then it will be like logistic, where outcome happened or not happened, and then you have got like explanatory variable and continuous. If I show you
okay. Understood, ma'am. Understood.
if you go to regression and if you go to binomial logistic, see here there is only one dependent variable and there are two boxes. Can you recall? Here you have to like put yes and no. It is not two, but in case of a Cox, you will find there are two boxes. Why?
Yes.
Because you have got, that's why it is a separate type of data which is known as the time to event data. You don't have only event. When that event happened, that is also important. That's why for survival, I'll go again up. You will see that there are two boxes, one for time elapsed, and this is TTE, which we call as a time to event data, TTE. So when that event happened and whether that event happened or not. So two dependent variable. When that event happened, an event can be event or sensor. So that's the total of this variable. If you come to data, this time to event, if you see this one, So what is this 37? That means in 47 days, the mother terminated the exclusive breastfeeding. In 118 days, the mother terminated the exclusive breastfeeding. In 74 days, the child was lost to follow-up. Am I making sense, Dr. Ravi?
Understood, ma'am. Understood.
Okay, thank you. So, coming to this time to event here in the time elapsed, an event happened or not happened. So, event I'll put it here. And then coming whether it is a censored. So, we want for termination of exclusive breastfeeding. So, that's why it is exclusive breastfeeding here. Now, I'll move variable one by one because I have to check whether in the unadjusted hazard ratio, what is the p-value? So if p-value is more than 0.2, then we will not take those variable in our model. Same way of the way we did in logistic. So I'll start with this gender of the baby. So I'll put that here in the explanatory variable. And it will give, for Cox, you need to come here. This I'm not using. This advanced elapsed time, we have seen that day that it is used when you have that start and end day. You can use that. Or you can use to change the output of your graph days. Analysis with multiple outcome, this we are not using. Plot, if you see plot, this I'm not using now. Now coming to, so without that only it gives you, it automatically whenever you move this variable, it gives you a, this is your unadjusted hazard, univariable. It gives both uni and multi, but since value will be same since only one variable is there. So it is 0.2. So if you see the gender, so I will include all and then we can see which all variable are. So this is 0.82. Sorry, 0.2. 0.82 is the hazard ratio. If you see gender has got a p-value of 0.2. Now I'll move this back. I will see with the marital status. So if you put marital status here, again, the value is 0.01. So marital status is also significant. 0.01, so I'll take this. Now coming to breastfeeding education, number of sessions. I'll put that in a continuous one and see the p-value. So p-value is significant. I'll include this also. Breastfeeding with it, then skin to skin contact. This I'll move back. Skin to skin contact, again enter this and see the p-value. P-value is 0.04. Again significant, I'll include this. Then breastfeeding within 1 hour. This is again significant, I'll include that again. Perception of breast milk. Let me see perception. If you want to include it as an ordinal, then you can. Let me see what is this Q then. Oh, it was the quota. No, Q, I think it's not needed. Let's delete this. And if I go, okay. This was, if I want to include it as a continuous variable, I need to change the nature. So it is a continuous for me. So now I'll go here. And again, you can take this perception of milk. If you take this, again, this is not significant, 0.8. So you may just, it is not, you will not include that. And then comes the gestational age. Gestational age is again, it is significant, you will take that. Then you take birth weight. Birth weight is again significant. So all variables are significant except for your perception of milk. So I'll take all the variables. Now coming to the second assumption, this is just what all variable I will take. Now again I have to check for two assumptions, that is the multicollinearity and proportional hazard. So how I will check for that? For proportional hazard, you can enter all the variable together and see. But for multicollinearity, you cannot check it from this. So I'll go to the logistic, binomial logistic, and then you can have this event as a dependent variable, and then you can include like covariate. So gender I will have here, marital status, education, breastfeeding, skin to skin, breastfeeding within 1 hour, perception of milk, gestational milk production, no gestational age, and birth weight. And if I go and see the assumption check, collinearity statistics, and see the VIF. So if you see gestational age and birth weight, both are having a value of more than 10. Rest are all okay. So you will have to remove these two variables. I mean, they are multicollinear, both are having value more than 10. So you have to keep one variable out of that. Either you can keep gestational age or you can keep birth weight, because they are showing collinearity. Now I'll again go here, and then now I have to check. So I have checked for the assumption of multicollinearity. Now I will go for the proportional hazard. So proportional hazard, how you will check? You include all those variables. So I will have all my significant variable, gender, marital status, education, breastfeeding education, skin to skin contact, breastfeeding within 1 hour, perception was not significant. And right now, let's say I'm taking the birth weight. So I'm taking, or let's say I'm taking gestational age. We'll see both these two, but just we don't have to enter these two together. And now I will go. It gives you all the univariable and multivariable, but because before I put that into the model, let me go to this plot option, not this one. Oh yes, there's this proportional hazard assumption. Can you see this plot? Proportional hazard. So this they have added new. The workshop which we conducted in 2023, which was the third survival, at that time this was not added in Jamovi. So we demonstrated using the SPSS, that is log minus log curve. But now they have added here in Jamovi. So if you come down and check, so this is your p-value, the overall test. Remember, we discussed that you can have that. So if you see the p-value is very, if it is writing e to the power 1, e to the power 2, that means those many points it will be like towards the left. So the p-value, if you see the global p-value, all this one, for individual variable. So for this, it is more than 0.5 because it is 0.8. If it is e to the power 2, then it is 0.05. Marital status, if you see, it is not 5.05. Yes, it is not. That means it is it is not meeting the assumption of proportional hazard. If you see the education, again, it is no, it is not meeting. But this 9, 7, 9 is again not meeting. Breastfeeding within 1 hour, it is meeting. And then 8.8. I don't know why this is giving the p-value as, because I think it will be difficult for you to interpret it. It is not. Is there any way to change this from output now? P-value format. No, less than 3 though it doesn't give. No, minimum is 3.
नंबर फॉर्मेट
This is again 2.
उसका फॉर्मेट बना देना डेसिमल 5 पॉइंट कर दीजिए 4 5 कर दीजिए
Will it change? No, it is not changing. Because it is like E, you have to reduce like it if it is 0, 1, 0, 2, 0, 5, this 1 0 will be added here. So it will be like 0.8. So you will have to like modify, I think why it is coming like this. Just a sec. No, so you have to interpret. So are you understanding how we interpret it? So this means if it is e to the power 0, 1, that means you have to put 1. This will be like 0.8. 0.8 because 1 point you have to move. This will be like 0.05. This will be like 0.4. This will be like 0.430 will be added here. So this will again, so if you see the proportional hazard assumption, this will meet the proportional hazard assumption 101. This will meet, and then this breastfeeding within 1 hour will meet. This will meet, others won't. So only wherever this value of e to the power 01 is there, then that assumption is met. This was regarding the objective way. Coming to the subjective way of that graph, this is the graph. So here you see that line is approximately like straight line. If you see the other two, this is a wavy one. So the this skin to skin contact, it is not. Again, this is not a straight line. This seems to be a straight line, this one. Marital status. If you see this gestational age, this also seems to be more of a straight line. So if you see from this, so there will be 4 variables which we discussed, which are, and this also you can, okay. So it is giving you individual test values.
Ma'am, could you please explain that E? I mean, how do you exactly
that? Okay. Don't. This here it is giving you. Don't see that table because E means that much decimal it shifts, but I think it will be difficult for you people. So just see this value 0.87. Actually,
0.2, if it is more than 0.2, then it is not
no, not
significant.
0.2.
So the
see this E1
Schonfield.
E1. Okay,
Schonfield.
This one.
I'm talking about Schonfield.
Yeah, this one. It is 0.8. So if it is more than 0.5, it is not 2. 1 is for 0.05. Sorry, if it is more than 0.05, that means not significant. Then this proportional hazard assumption is met.
So in this case, it is not significant. So hence, the proportional hazard assumption is being met.
Yeah. So you can take this variable in your model. So what all you can take? Gender. I'm writing it separately. You can take gender. Come down. You see this value. Skin to skin you cannot take because its value is 0.01. 0.001. So you cannot take. Again come down. This is 0.01. Gestational age you cannot take. Now go right and up. Why it is giving only for 3? Let me check. 1, 2. No, it is coming. Here it is. When you scroll it towards the right now, this is for the marital status. Many times now. होता नहीं है इसको रुको. Now you can see. This is your 0.8 for gender. Again, if I move towards the right, this is 0.05 for marital. We cannot take marital. This is your 0.4 for mother's education. So gender and education. At these two, the proportional hazard assumption is met. Then if I start from here only, point 8 is breastfeeding education. This one. This is point 8. I can take that. So mother education and breastfeeding education, both proportional hazard assumption met. Then I will go towards the left. This is point 7, which is breastfeeding within 1 hour. So early initiation, proportional hazard assumption met. So I took it. This value is 0.001 and the variable is skin to skin. I am not taking skin to skin. Go down, 0.01 gestational age. I cannot take this. And then you scroll towards the right to see if any other variable got missed. So no. So out of how many variable? Let me. One, two, three, four, 5 to 7. Out of 7 variable, 4 variables met the proportional hazard assumption. Gender, mother education, prenatal education of breastfeeding, and the early initiation of breastfeeding. Have you understood up till this point? Then I'll move ahead. Dr. Ravi, Dr. Priyanka, I don't know. Am I making sense to all of you? Actually, initially I was explaining this one. There's a difficulty in explaining this e to the power 1 because you will have to convert it into decimal. So it's better that you see the value which is lying here. Yes, Tanya?
Ma'am, where can I find the residual graph? In which of the left side? I can't find it.
This proportional hazard assumption.
No, miss. Yes, proportional hazard assumption, the graphs. Where can I find them?
Yeah,
वर्षन क्या था
okay, yeah.
Okay, ma'am, I found it. Thank
This
you.
one. Okay.
Thank you.
Under the plots.
Yes. Thank you.
Welcome, you're welcome. And if you have understood up till this point, then I will not have other variable. And this was one way of, so there are 3 criteria of taking the variable. First one, I will see the univariable. So if I see the p value, I can include the gender because p value is up till 0.25. I can have marital, I can have this thing. All are okay. So I can have all the variables. And multivariable, then the second one will be proportional hazard. So the proportional, then multicollinearity, I have removed one variable, that was the gestational birth weight. I did not take that. And then there was another one, which is the proportional hazard. So I will have only gender. So what I'll do, I will move this marital status back to this window and skin to skin again back to this window and gestational age also back to this window. So there were only 4 variable for which I will make the model. And then I will go down and then you can have this hazard regression plot. You can have this Kaplan-Meier. Kaplan-Meier I'll show later. You can have this, this is regarding your plot. If you click this Kaplan-Meier, then only you have to change this the way we have done, like 180 days. Time interval will be your 30. Median line if you want to put. And cut points if you want to give like 30. This we did on day 1 and day 2. 30, 60, 90, 120, 150, 180. This is risk score. I am not showing you this risk score. Adjusted survival analysis. If you wish to have an adjusted survival curve, then you can click that and you can see like which variable do you want to adjust. So you can only adjust one variable. Suppose this we'll see later after we have understood this curve. Stratification, nomogram, person time. So first I'll explain this. So this gender, it gives you like 0.8 with this inclusion of all other variables also. The value is same in multivariable and the univariable, but it is not significant. So you can say that there is 17% less hazard in female as compared to male of experiencing the event, but that is not significant. If you see the education, it is significant. And if its value is 0.67, how will you interpret? Hazard ratio -1. So 1 minus 0.67, that means it will be your 33%. So there is a 33, and since the sign is negative, or if it is less than 1, we can say that the women who are having lower education, they are having 33% less hazard of experiencing the event as compared to the women who are having higher education. Similarly, if it is 0.51, I can say that the hazard is 0.5 in women who are breastfeeding within 1 hour of the baby as compared to the women who are not breastfeeding their baby within 1 hour of delivery. That means this is a protective. This is again protective. This is protective, means less education, less experiencing the event. And this is breastfeeding education, means the number of sessions attended in the prenatal period. So if you see, it is
Could you
1.16.
just come back to the education again, ma'am? Because could you just come back to the education again?
Yeah, this one.
Yes, please.
Yeah, please ask Dr. Ravi, what is the issue?
Ma'am, the lower the education means it is protective.
Yes. I mean,
Strange, but
that's the
that's the finding of their study. Okay, fine.
I mean, it's actually dummy data, so you cannot
Fine, fine, fine,
see it with
fine.
the real life implications.
Understood.
Dr. Tanya, yes?
Ma'am, is there any specific number in the Schoenfeld residuals that helps me to take it as in the model or discard it from the model?
Proportional hazard. P-value,
Yes.
if it is more than 0.5, then you will take it in the model because that says that that variable is time independent. That means that
Okay.
variable was not changing with time. That's why the p-value is more than 0.05. So if the p-value is non-significant, that means you can take that variable in your model. Otherwise,
That
you
means
cannot
if
take.
the p-value is more than 0.5, I will take this.
0.05, 0.05.
More
than
than.
0.05. Yeah, we take the
Okay.
significance of 0.05 now. So that means your
Yeah.
p-value should be more than 0.05, not 0.5. Sorry.
Okay, ma'am. If it is more than 0.05, then I will put it into the model of proportional hazard assumption.
Yeah.
Otherwise, I cannot take it in the model, right?
Yeah.
Okay,
True.
thank you, ma'am.
And all the model metrics, if you see, okay, it gives you this thing also, like plot, hazard regression plot also, which I clicked here in this option. This one, hazard regression plot. If you come down, this was proportional hazard assumption. For Kaplan-Meier,
Ma'am, the gender of baby is including one right on top in the plot what you have shown. So that will not be significant, right? Ma'am, below. Yeah, above, just above. And the plots, the metrics, ma'am, just is above this. Yeah, hold. Below, ma'am, below. Yes, just the one is included in male and female. So obviously, as per this,
it was
this will
not
not be
significant. Na?
significant.
This is there. You can see the p-value. It is 0.2.
Yeah, it's not significant. Okay.
Yes, Dr. Richie and Dr. Tanya.
Ma'am, in the Schonfield plot, I think one of them was 0.050. I mean,
Okay, let me check. Let me check. I might have made some mistake. This is gender. This is 0.9. So it is more than 0.05. Then this is your breastfeeding within 1 hour. This is 0.7. So it is more than 0.05. Then I will go towards right. This is education, mother's education, and the value is 0.4. So I will include it. If I come down, this is your breastfeeding education, number of sessions. It is again 0.8. So I'll include that. I have moved towards the right here. You will not find, I think, up there will be one. So I think all these are, right now it is not showing the other variable. It is only showing the variable which I have included. If Richie, you wanted to talk about which variable?
ma'am, actually, I missed that. I can't remember, but I think one of the middle, like I think the
Okay.
third or fourth
Let
one.
me move. No, that has all gone back into this window. No, it will not show. You will have to move this again back to. So
In the gestational age, the p-value is 0.03.
Okay, just a sec. Dr. Richie, I just after this Tanya's question, I'll move all the variables back to this window and then we can see again.
Yes, ma'am.
Okay. Yes, Dr. Tanya, what you were saying something.
In the proportional hazard assumption, you have put into the gestational age, but the p-value for the gestational age is 0.03. It is
Okay.
less than 0.05. So can
Yeah.
we put it?
You are saying the p-value where? Univariable hazard ratio or the Schoenfeld residual?
Schoenfeld.
Schoenfeld, I have put, no, I did not put gestational age.
Okay. Okay, ma'am.
That's why in
Thank
the final model, you can see gestational age is not here.
Okay, ma'am.
Did I put that? If I put that, I think it is by mistake because gestational age was not there. But again, since Dr. Richie is asking, I'll move all the variables. I will move this gestational age here. And I'm not moving birth weight. I will only take one of these variable because these two were having multicollinearity. So that's why either you can have gestational age or you can have birth weight. So I'll see this, let's say right now if I'm taking this birth weight and I'll have other variables also like marital status, skin to skin contact, perception of milk I am not taking because that I removed on the basis of univariable. Univariable means I check the p-value here in the univariable and if any variable is having value more than 0.25, I will not take that into the final model. So maybe I'm trying to make the final model, but for that I need to check for the assumption of proportional hazard. So I check that and now I will see Dr. Richie what you were talking regarding the Schoenfeld. So let me enlarge this. Data. So this is one. The first your gender of baby. Value is 0.8. Then your education. It is again beta for education. This is your 0.4. And breastfeeding within 1 hour. This is 0.6. So all these three met the assumption of proportional hazard. Coming down, this is 0.04. So marital status, it is, you can see, this is not meeting the proportional hazard. Okay. And then if you come skin to skin contact, this is also not meeting the proportional hazard. It is e to the power 0.4 means 3 0 should be added here. And this is also 0.04. So birth weight is also 0.04. So not significant. I mean, it is significant. So this is not meeting proportional hazard assumption. Is it clear, Dr. Richie?
It's clear, ma'am.
Okay. Thank you. So, and again, go to the data. And now I will move this because in this thing only breastfeeding education was there. That's why I'll move all these variable back. So marital status, skin to skin contact, only 3. Gender, maternal education, breastfeeding education, and early initiation of breastfeeding. Only these 4 variables. We have plotted that. Then for Kaplan-Meier, it is only for 2 explanatory variable. So if I will have to move other variable to this window, then it will give me the. So I'm just skipping this for now. And then adjusted survival curve, you might, if you want to adjust it for, let's say, gender of the baby, then you may get adjusted survival curve. So it will show you the average adjustment. And this shows like you will have to so this adjusted survival curve, they don't have that color coding. But again, that's why it is not clear. But let's see if there is some solution to it. And then that is no. No, it is not here. That upper one, if you like plot it, then they have this thing. If you only have the survival curve for 2, let's say, if I move these 2 variable and I only see the gender and education, then I may have this Kaplan-Meier for 2 explanatory variable, where you can see the survival probability for one factor being adjusted with the other. Let's wait. I think I'll explore this more. This is on the basis of
gender option मिला करके
yeah, this will give you 4 combination: gender baby male and higher education, gender baby male and lower education. So all 4 combination, because 2 explanatory variable will have 4 combination, and log rank test was this thing significant. So you can see the color. This is having a higher survival probability, like female baby having lower education, and the lowest is for this blue one. That means male baby with the higher education, the lowest survival probability. So this is your adjusted. When you want to see for the 2 factors together, then you can use this for 2 explanatory variable. This one adjusted survival curve, if I can see, it is not giving you the color. And then if hazard you have seen, hazard regression plot. This was your hazard regression plot. Okay, so I think till now you can practice up till this point, and there are few other options which we will tell you tomorrow, like the advanced analysis, like stratification. That means, remember we discussed that variables which are not having the proportional hazard assumption, you can stratify. So use of stratification and the person time. This we'll see tomorrow. So before we conclude today's session, I think you all go to the breakout room and practice for 15 to 20 minutes, and then we'll see. So Anand is here. You are opening the breakout room.
Yes, ma'am, I'm there.